Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the phase diagrams for binary eutectic systems. So in this study, we will discuss about what is the importance of the phase diagrams and what are the different types of phase diagrams and how do we define different types of phases with respect to the microstructure as well as the properties. So how these phase diagrams will impact the microstructure as well as the properties of the any type of material given to us. These phase diagrams are very important. Now if you see the phase diagrams, the understanding of phase diagrams for alloy system is extremely important because there is a strong correlation between the microstructure as well as the properties of the material. So what is the importance of studying these phase diagrams means? This phase diagram help us to give the correlation between the microstructure as well as the mechanical properties of the given alloying material. And the development of microstructure of the alloy is also related to its characteristics of the phase diagram. So whatever the characteristics you want to get from the alloys, so this also depends upon the phase diagrams. And also we have a correlation between the material properties as well as the microstructure of the given alloy. So if you study the phase diagram, if you understand the concept of the phase diagram, it is very easy for us to how to relate the relation between the microstructure as well as the mechanical properties, and also how the development in the microstructure can also be studied with the help of these phase diagrams. So not only these three informations what we'll get from the phase diagram, additionally we can get the valuable information about the melting, casting, crystallization and other phenomena. So if you want to do any casting process, you have to know the melting temperatures of the given material. So how can you get those temperatures means with the help of the phase diagrams. That's why the phase diagrams are not only restricted for the development of the microstructure or also the mechanical properties as well as the microstructure. So apart from these three things, we can also identify the melting temperature of the given material, also the casting process, the crystallization temperature and other phenomena. So these are the additional information what we can get from the phase diagrams. That's why phase diagrams are very important. So once if you know the if you can understand the concept of the phase diagram, it is very easy for us to know the different temperatures, how the material is behaving. So that is very important. So a different interval of temperatures. So how the material is changing with respect to temperature. So this can be studied with the help of the phase diagrams. And also how the material is converting from one phase to other phase. So this also can be studied with the help of the phase diagrams. So that's why the phase diagrams are very important. So all this combines us to know the characteristics of the given material. So if you want to know the characteristics of the given material, it is very easy for us to get these characteristics with the help of the phase diagrams. So that's why the phase diagrams are very important. So if you see the graph as shown in this figure, so here we are taking an example of H2O, that is the water, to explain how the phase transformation is happening at different stages with respect to the temperature. If you understand the basic concept of the water phenomena changes in the phase diagram, then it is very easy for us to further any given material, how the material is changing or how it is being transforming from one phase to other phase with respect to temperature. So that's why we'll consider an example of a base water. Okay, this H2O will consider a pure water. From this pure water, we'll see how the phases are being transforming from one phase to other phase with respect to the temperature. Now, what are we doing here? We are plotting the x and y axis. So if you see here, along the y axis you have the pressure. So this is the y axis what we have, and if you see the along x axis, it is the temperature. Okay, temperature versus the pressure. So these are the values what we are having along the y as well as the x axis. So in this sense, what we are doing, we are trying to draw the diagram. So how the phases are being transforming of the pure water with respect to at different temperatures. Okay, so you have the three red curves here. One is the one, and the other is the total three red curves here. So what are these three red curves represent? So these are the boundaries of each phase. So what is general happens for the water? So initially it is in the a solid phase. That means the ice in terms of ice. So that is in the form of a solid phase. Now slowly if you uh, the solid phase, it has a minus degrees temperature. So that's why if you see here, the temperature is around the minus 20 degrees centigrade. So at minus 20 degrees centigrade, the water will be in the solid state. So pure water will be in the solid state at minus 20 degrees centigrade. Now, what you're trying to do, we are slowly increasing the temperature. If you see here, there is a rise in the temperature along the x-axis. So from minus 20 to 0, 0 to 20, 40 like that, we are increasing the temperature along the x-axis up to 120 degrees centigrade. Now, if you increase the temperature from minus 20 to say about 0 at 0 degrees centigrade. So what is happening? What are the solid form of pure water is there? It is slowly trying to convert into a liquid phase at this point of 0 degrees centigrade. So this solid state is being converting into a liquid state. Liquid state. So that is the transformation of one phase to other phase. What is happening here? From the solid state, what are the pure water is there? So this is a solid phase at minus 20 degrees centigrade. This is slowly converting into liquid phase when you increase the temperature up to 0 degrees centigrade. Okay, so this is the another phase what we have from solid to a liquid. Now, if you still increase the temperature, what is happening? If you raise the temperature along the x-axis, so this liquid, whatever the liquid you have, it is slowly converting into a vapor. That is nothing but the steam. That means a gaseous phase. So what is happening here? If you still increase the temperature, say about 100 degrees centigrade. So this liquid state is converting into a vapor or steam. Okay. Sorry. You can see in this picture very clearly. So what is happening here? At minus 20 degrees centigrade, we have a solid phase. This is the solid phase what you have. And if you increase the temperature at 0 degrees centigrade, so what is happening? So this solid is being converting into a liquid phase. Okay. Now this liquid phase, if you still increase the temperature, if you raise the temperature, it is coming into a vapor. So these are the three different phases what you have. And these red lines what you're indicating are the boundaries of each phase. So if you cross the boundary, what is happening? The liquid phase from solid to liquid, it is converting. Okay, so it is the boundary. So where the phases are being changing from one phase to other phases. So totally you have here three different boundaries in which three phases what we have here as solid, liquid and gaseous, that is the vapor phases. So this is how you can draw the phase diagram with respect to the temperature as well as the pressure. So this is the concept of the phase diagram. So with the help of this phase diagram, what can you infer? What can you infer is, I can easily tell that the water can be in a solid state at minus 20 degrees centigrade. So with the help of the phase diagram, we can easily tell that the water can be in a solid form at minus 20 degrees centigrade. And the same solid of water can be in a liquid state at 0 degrees centigrade. So all these things we are trying to tell from the help of the phase diagram itself. And next is what? The water can convert into gaseous or the vapor zone, vapor phase above the 100 degrees centigrade. So that is how you can easily tell that what is the property of this material, at what point the water is being melting, at what point the water is getting into gaseous state, as well as at what point, at what temperature the water is in the solid form. So all these can be inferred with the help from the phase diagram. That's why the phase diagrams are very, very important to characterize the given material, and also it will give the mechanical properties of the material and also the melting temperatures of any given material. So this is how you can draw the phase diagram. And if you further go inside the phase diagram, so you have some basic definitions like what is a component. So what is a component means the term component are the pure metals. Okay, the component is nothing but a pure metal or a compound which is composed of some different types of alloys. Okay, so that is the basic definition of a component. Now, a system. What is a system means? The system may refer to a specific body. Okay, here component is nothing but a pure metal. Okay, component is nothing but a pure metal, and here system refers to a specific body of material under consideration. So, what are the material we are considering to perform any operation? Okay, so this material combinedly it is called as a system. And for many alloys systems at some specific temperature, there is a maximum concentration of solute atoms that may dissolve in the solvent, okay, to form a solid solution, and this is called as a solubility limit. So what is solubility limit means? So in any given system, what is happening? There is some maximum concentration of the solute atoms. So you have some solute atoms inside the system. So these solute atoms may dissolve at some extent, at some point of extent. These solute atoms, whatever the solute atoms are present in the system, can be dissolved. And what is happening after crossing some limit? These solute atoms will not dissolve in that system. Okay, so there is a limit of these solute atoms which may not dissolve further in this solute. Okay, so that is the definition of the solubility limit. Solubility limit is nothing but the whatever the solute atoms are there, they may dissolve in the system, in the solvent, and after further if you still add some solute atoms in the solvent, they may not dissolve. If you take a simple example of water and sugar, so what happens here? If you add some sugar in the water, it will dissolve for some time. And still, if you add some more sugar into the water, what is happening? The density of the water will increase, but at some point of time, these sugar crystals will also dissolve in the water. Okay, so what is happening? Slowly, the water is converting into high dense material. The solute is becoming very thick thing. Now, after that third time again, if you add some sugar into the water, what is happening here? The sugar will not dissolve. Why? Because the properties of the water is becoming diverted. What are the solvent we have? That is completely converting. So here you have the limit. So beyond that limit, whatever the solute you are adding in the solvent will not dissolve. Okay, so that is called the solubility limit. And the addition of solute, if you see the second point here, the addition of solute in excess of the solubility limit results in the formation of another solid solution or compound that has a different composition. So what is happening? If you still add some more solute to the solvent, what is happening here? This will not completely solve in the solvent. What is happening here? There is a formation of other solid solution. What are the example we have discussed earlier of the sugar as well as the water? So we are getting some thick layer of the dense sugar syrup. So this is forming another solid solution. So that's why there is a limit, there is a solubility limit. After crossing the solubility limit, though you add some solvent to the solute to the solvent, this will not be dissolved in that solvent. So the same thing to explain what is the concept we are discussing about the solubility limit. So we are taking an example of the sugar and water here. So initially, as sugar is added into the water, what is happening? Sugar and water forms into sugar syrup. So initially, I have a glass of water. Okay. So what I'm trying to do here, I'm adding these sugar. So what is happening here? After some time, these sugar, what are the sugar I'm adding, will be soluble, and again it forms as a liquid. And what is happening? What are the initial liquid is there? The water. It is slowly changing its density. The thickness of the water is increased because of the sugar what we are adding. So what is happening here? Water solution or some syrup is formed because we are adding the sugar into the water. Now what is happening further, as more sugar is introduced, what is happening here? The solution becomes more concentrated. So what is the solution is there here? It is still becoming more concentrated because the addition of the sugar into this water. The concentration is becoming very, very high until the solubility limit. So until the solubility limit is reached, what are the solute you are adding into the solvent will be dissolved and the concentration is being increased here. Okay. Now, after that, what is happening here? At this time, the solution is not capable of dissolving any more sugar. Why? Because the thickness of the water is very, very high here. The concentration is very, very high. That's why though you add still sugar into the syrup, it won't dissolve into that syrup what you have. And further addition simply settle down at the bottom of the container because it is not being dissolved into that syrup. What is happening? Slowly it is coming down and settling. So like this. So these are the concentrated syrup what we have. And since you're adding, so these sugar crystals are being settling down at the bottom of the container like this. But this won't dissolve. Why? Because you have a high concentrated sugar syrup. Thus the system now consists of what is happening? Two separate substances. Since it is not being solved into the solvent, what is happening? Here we have two separate substances. What are the two different substances you have? Sugar syrup as well as the sugar whatever it is being settled at the bottom. So 1 and the 2. So total 2 substances we are getting after reaching that solubility limit. Okay. So what is that? A sugar water syrup which is in the liquid solution and the solid crystals of undissolved. So these are the two things what we get, two substances what we get after reaching this solubility limit. So this solubility limit of sugar in water depends upon the temperature of the water and may be represented in graphical form. So whatever the solubility limit after reaching, again what are the crystals you have? These are not dissolving. So this can be dissolved again, which depends upon the temperature. Now if you increase the temperature for this, suppose I am increasing the temperature around 80 degrees centigrade. So what happens? The concentrated, the thickness of the syrup will be diluted and the sugar can be dissolved in that. So this is how again the temperature plays a key role in this depends. Okay, how to dissolve these sugar crystals. Now if you plot the phase diagram, so here along the composition axis increase the sugar concentration. So along the x-axis we are starting with 0 of sugar and slowly we are increasing the sugar concentration from 0 to 100 degrees centigrade. Now in the similar way in the reverse direction we are adding the water from 0 it increasing to 100. So wherever you see the total percentage, it should be 100. So if you see here, the total weight percentage of the water as well as the sugar should be 100. That's why you're starting with 0 of sugar and 100% of water at initial state. It's not. As we discussed at initial, we're just adding in 100% of water, 0% of sugar. Slowly now you're increasing the percentage to 20% of sugar in the water. So what is the remaining? 80% will be your remaining of water. Like that, if you still increase to 40% of sugar, what will be the total percentage? The remaining percentage of water will be 60. So always the total concentration of the sugar as well as the water should be 100%. That's why if you see the along the x-axis composition weight percentage, wherever you see you will have the 100 weight percentage. So this is you have to remember very carefully. And of course along the y-axis you have the temperature. Now if you increase the temperature as we discussed in the previous slides, the solubility limit can be increased. Now at the initial position you have the liquid syrup. Okay. Now what is happening? If you're adding sugar slowly, this is dissolved Now after reaching the solubility limit, what is happening? You have two solutions I told. Here, first one is the liquid solution, which is having the complete syrup of the sugar. And the second one is what? After reaching that solubility limit, there is a solid plus liquid syrup. So two solutions, two things we have in this. So this is how you can draw the phase diagram for the sugar and water. The solubility limit is represented as a nearly vertical line. If you see this solubility limit line, it almost looks like a vertical line. And the composition and temperatures which are shown on the left of the solubility limit. So these are the along the left. So at this point, before the solubility limit, you will have the percentage. If you want to know the percentage of the water and the sugar before the solubility, what I have to do? I have to draw a line vertical like this, so that I get the composition at this point, and the temperature at what are the temperatures, at what temperatures. So like this I can get. So like this, if you drop the vertical lines along the composition, you get the composition percentage, and if you draw the horizontal lines along the temperature, you get the temperature corresponding to that composition. So like that, you can easily find out what is the composition along that temperature. Now, for example, at 20 degrees centigrade, the maximum solubility limit of the sugar is 65 weight percentage. Now if you see the at 20 degrees centigrade, if you see the 20 degrees centigrade, I have to draw a horizontal line like this. And now if you see the percentage at this point, it is a 65 weight percentage. 65 weight percentage of sugar, and what is the remaining? It is 35 weight percentage of water. Okay, 65 and 35 percentage. Total will be again 100 percentage. So at this point, if I want to know the composition at 20 degrees centigrade, I have to draw a horizontal line like this to the solubility limit, that curve. And if you see the percentage of the sugar as well as the water, you can easily get like the 65 weight percentage of sugar and 35 weight percentage of water. Similarly, if I want to know at this 60, again there is some change. Here I might get 70 weight percentage of sugar, and the remaining will be 30 weight percentage of water. So at 60 degrees centigrade, I am having the composition of 70 and 30. At 20 degrees centigrade, I have 65 and 35. This is about the sugar and this water. So like that, at different temperatures, we can get the compositions of the sugar as well as the water. Like this, for any given type of alloy or any type of material, you can easily find out the compositions, or what are the temperatures, or what are the solubility limit, and what are the different types of phases you have with respect to these phase diagrams. That's why these phase diagrams are very, very important in describing or in characterizing of any given material. Also, critical to understand of the phase diagrams is the concept of a phase. So as discussed, this phase is very, very important. Once if you want to describe any phase diagrams, the phase is very, very important. So what type of phase you have, whether you have a liquid phase or solid phase, or combination of liquid as well as solid phases. Okay, based upon these phases, you can easily draw these what are the boundaries are there. Okay, if you draw the boundaries, then you can easily tell that at this boundary we have the liquid zone, at this boundary we have the solid zone, and at this boundary we have the gaseous. Like this, the phase understanding is very, very important in understanding the phase diagrams. And also, a phase may be defined as a homogeneous portion of a system that has a uniform physical and chemical characteristics. So each phase, it has its own physical as well as the chemical characteristics. So once it transforms from one phase to other phase, again these physical as well as the chemical characteristics may differ. That's why each phase has its own physical as well as the chemical characteristics. Every pure material is considered to be phase. Is it not? Every pure material is considered to be in phase. So after that, depending upon the temperature, this pure metal phase may differ from one to other. Okay, so it is like that, converting from solid to liquid, liquid to gaseous, like that. So as we discussed, the sugar water syrup is the best example to describe these phases, in which you have only two types of phases, that is the solid as well as solid plus liquid. And coming to the water, it has the three phases of solid, water and the gaseous, and each has its own physical properties. Liquid will have its own liquid properties, solid will have its own solid properties, and gaseous will have its gaseous properties. So if more than one phase is present in a given system, so what happens, as we had discussed in the sugar and water syrup, each will have its own distinct properties. Again, a system which is having two types of phases, so what is happening here? Again, these two phases have its own distinct properties, and a boundary separating these phases will exist across there, and it will discontinue the changes in the physical as well as the chemical characteristics. So when these two phases are present in the system, what is happening? It is not necessary that there will be a difference in the physical and chemical properties, but in one or the other, a set of properties is sufficient. Okay, so though we have two different phases in a material, it cannot be true that one may have the different properties, another may have different properties. Okay, so when water and ice are present in a container, two separate phases exist, and these are physically dissimilar when they look like a solid and the liquid phases, but identical in chemical makeup. So that is the thing what you are trying to tell. And sometimes these single phases, it's termed as homogeneous. So homogeneous means a single phase. It has a uniform structure. And systems composed of two or more phases are termed as mixtures or heterogeneous. So homogeneous means a single phase. Heterogeneous means more than two phases. Then the types of systems are called heterogeneous systems. So most metallic alloys, for that matter ceramics, polymers, and composite systems are heterogeneous. So what are the new different types of materials we are getting, the new trend? So these are all the combination of different materials. So these will have different phases present. That's why these are all comes under the category of heterogeneous materials. The composite material, the ceramics, the polymers, all these comes under the category of heterogeneous. So homogeneous material very, very less, which is having a single types of phases. So ordinarily the phase interact in such a way that the property combination of the multiple phase system is different from the more attractive than the individual phases. So because of the two different phases present in the material, what is happening? The properties are being enhanced. So because of these multiple phase systems, so what is happening? There is a more attractive of these properties when you compare with the single phase things. The single phases will have less properties when you compare with the the heterogeneous types of material, because it is having a multiple materials which has the multiple properties when you compare with the individual materials, so that these strength wise the mechanical properties will be very, very high, very good in the sense when you compare with the single type of homogeneous materials. And coming to these phase diagrams, what is happening? Again, you have a binary phase diagrams and unary phase diagrams. So what is unary phase diagram is one component. So whatever the phase diagrams you have, it is having two classifications of the phase diagrams: unary phase diagram and as the binary phase diagram. So unary phase diagram is nothing but the one component phase diagram. So one component, only one component which is present in the phase diagram, then the type of system is called as a unary phase diagram. So much of the information about the control of the phase structure of a particular system is conveniently and concisely displayed what is called as phase diagram. So this phase diagram is very, very important to study the characteristics of the given material. Now there are three externally controlled parameters which will affect the phase diagram. So what are the three control parameters you have here? Temperature, pressure and the composition. So if you see the phase diagram in the earlier slides, so what we have drawn, based upon the composition, based upon the pressure, based upon the temperature, we have drawn the phase diagrams. So the pressure, temperature and composition are the three parameters which control the phase structure of any given material. So these are the three parameters. These are the three externally controlled parameters. So we can control these. We can increase the temperature. We can increase the pressure. We can change the composition. We can vary all these things. That's why these are called the externally controlled parameters which influence the structure, the phase structure of the given material. So the phase diagrams are constructed when various combinations of these parameters are plotted against one another. Is it not? Based upon these three parameters only, we are trying to draw the phase diagram. We are trying to draw the phase diagram, or we are plotting the phase diagram against one another. If you vary the composition, what is the temperature? Okay, if you vary the pressure, what is the composition? So in this, like this, we will draw the different types of plots against these, which are the externally controlled variables. Perhaps the simplest and easiest type of the phase diagram to understand is that for one component system in which the constitution is held constant, this means that pressure and temperatures are variable. So in this thing, one component means the one component will be at a constant here. So what is that constant here? Temperature, pressure are variables. That means composition is held as a constant. What is that? We are making this one variable as constant. That is, the composition we are making as a constant, and temperature and pressure, of course, these are variables. And since we are making one component, that is the composition, as a constant here, that's why it is called as a unitary phase diagram. That is the one component phase diagram. So this one component phase diagram or unitary phase diagram is also called as a PT. That means you are varying the pressure and temperature. These are the variables. Since P and T are variables in the unitary phase diagrams, that's why these are called as a PT diagrams. Since the composition is being constant, so these we are not considering here. That's why it is called as a PT diagrams. So another type of phase diagram what we have discussed is a binary phase diagram. So one component or unitary phase diagram, that is first one. The second one is the binary phase diagrams. Another type of extremely common phase diagram what we are drawing here, in which temperature and compositions are variable parameters and pressure is constant. Here pressure is constant and temperature and composition is variable. Okay, this type of system is called as a binary phase diagram. So binary phase diagrams are maps that represent the relation between the temperature as well as the composition. So since these two are the variables here, the temperature and the compositions, so what are the phase diagrams we are drawing in the binary phase diagram? This describes the temperature as well as the composition, and how much quantities of composition we have, at what temperature. All these things can be studied with the help of the binary. And coming to unitary, what is happening there? There we have only the composition as the constant. We will study the pressure as well as the temperature. That is the PT diagrams in the unitary phase diagrams. And coming to the binary, the pressure is being held constant and the temperature and compositions can be studied in this binary phase diagrams. Many microstructures develop from the phase transformation, the changes that occur when the temperature is altered. Is it not? When you alter the temperature, or when a system is coming from high temperature to low temperature, what is happening? There is a change in the temperature. Similarly, there is a change in the microstructure. Earlier it is in the solid state, slowly it is coming into the liquid state. So what is happening in the solid state? You have one structure, liquid you have another structure, in between also you have different structures. So there is a development in the crystal structure based upon the temperature. That's why temperature influences the microstructure of the given material. So upon ordinary cooling from solids to liquid state, when it comes, what is happening? Or from the liquid to solid, what is happening? There is a change in the microstructure. So this completely depends upon the temperature. So this may involve the transformation from one phase to other. That means from the liquid to solid state, if it is transforming, so it is completely from one phase to other phase. So the appearance or disappearance of these phases influence the microstructure. So the binary phase diagram help the predicting the phase transformation and resulting microstructure. So you have different microstructure in this case, and also in this case also you have different microstructure. So in this between the journey from the liquid to solid also you have different types of structures. So that's why the temperature is very, very important in identifying the microstructure of any given material. Next, binary isomorphous system. So possibly the easiest type of binary phase diagrams to understand and interpret is the type of characteristics that are for copper and nickel. So if you take the copper and nickel example like this, you have different types of examples. You can take the combinations of different compositions and you can easily find out the draw the phase diagrams, and you can easily tell how many types of phases you have, at what temperatures, at what compositions the metal is being changing, and what is the solubility limit. Everything can be get from the information from the help of the base diagram. Now you have the different phases here. You have the liquid phase and you have the solid phase and the liquid line. You have the combination of both. Okay, now if I want the what is the composition at 1400 degrees centigrade, what I have to do, I have to draw up a vertical line. Okay, so I'll get the composition is, so this composition will be 20 weight percentage of copper. Well, what is the other thing? 80 weight percentage of nickel, like this. Okay, now in this system if you have a single phase, then it is very easy for dropping like this. You can drop at any point and you can easily find out. Okay, at this point if I want, I can easily drop. But any phase diagram which is having a two phases, then you have to use the line diagram. So that we'll discuss in the next classes. But at some point at this point A, if I want the composition, just drop the vertical and horizontal lines at this point. So I'll get the temperature as 1085 at this point, and the composition will be 60 weight percentage of copper and 40 weight percentage of nickel. Like this I'll get. So this is how you have to draw the phase diagrams and identify how many types of phases are present in this. So you have a liquid phase here, you have a solid phase here, and these are the border lines of the liquid line, and this is the border line for the solid line, and in between again you have the alpha plus L, that means solid plus liquid. You have the combination. So two different things you have, and this is the point B. If you want to find out what is the composition at the point B, again you have to draw. Okay, you have to draw the lines, and like this you can draw and you can easily find out. Oh yeah, next one is binary isomorphous system. Next one, a couple of comments or in order to regarding the nomenclature, how to give the nomenclature. For the liquid thing, you are showing as L. For the solid, it is alpha. Alpha plus L is nothing but the combination of liquid as well as the solid. Okay, that is how the representation of alpha, beta, gamma. You can have different nomenclature based upon the things. So the solidus line indicated between the regions of alpha and alpha plus regions. So below that you have the complete solid phase, that is the alpha region. So if you take any type of system, any type of material, each material will have its own physical and chemical properties, and it has its own microstructure. Now when it is changing from one phase to other phase, so what happens? During the phase transformation, there is a change in the microstructure, and also there is a change in the properties of the material. So how do you get the information? All these things means with the help of the phase diagrams only. So once if you know the phase diagrams, then it is very easy for us to find out the what is the characteristics of the given material, what are the physical and mechanical properties of the material, and how to correlate between these things, and also how to get the melting and temperatures of the given material. So with all these things information, it is very easy for us to select the material for the different types of applications. So any material we are selecting means you have to know all the properties. So how can you know the properties means based upon these phase diagrams only. Now again, you have different types of phase diagrams based upon the classification of unary or binary. So in this unary phase diagrams, you have pressure and temperatures are the variables and composition is kept as a constant. And coming to the binary phase diagrams, in this what is happening here? The pressure is being constant and composition and temperatures are being varied. So like this, based upon the variations or variables or which is constant, you are classifying the types of phase diagrams. And from these phase diagrams, what can you interpret means you can interpret how many types of phases are present, and if you have a single phase, how to find out the composition as well as the temperature. And if you have two phases in a system, in a single system, how to find out these compositions as well as the temperatures also we can infer. So these are all the information we can get from the phase diagram. So if you go to the references from the Introduction to Physical Metallurgy by Sidney Havner and Essential of Material Science Engineering by Donald, and the Material Science and Metallurgy by Codigiri, and Material Science Engineering by William Castler. So these are some of the references where you can get the information of these phase diagrams and the classifications of phase diagrams, and what are the information can you infer from these phase diagrams, and how it is so important to study the phase diagrams and how to apply these phase diagrams to the real-time applications. All these things can be get from these references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.